Okay, so here's the Zoom meeting for Physics 232C. This will be the Zoom meeting to go over Chapter 15 and some of the homework problems in problem set 1. We'll always have the Zoom meetings Monday at 7 p.m., except for today. Today it's Tuesday at 7 p.m. But that's because Monday was a university holiday. But in general, we'll have the Zoom meetings Monday at 7 p.m. And the main purpose will be to go over some examples of the homework. So chapter 15 is on the electric field, also the electric charge, also the electric force. Those all go together. So you should be reading chapter 15, or maybe you've already finished reading chapter 15. And it's important, take notes. You should read the chapter. That's probably going to take several hours. As you read the chapter, take notes in your physics notebook. I would say for each chapter, you should have about 1 page of notes, front and back. Mostly equations. Most of the notes will be equations, maybe a few figures. So for chapter 15, you need to understand electric charge. So, this is something you might have taken a note on. What does that equation mean? Well, it means that all charges are integer multiples of a fundamental charge, which we call E. E could be considered to be the proton charge, or it could be considered to be the negative of the electron charge. Electron charges are negative, so minus E, negative E, would be the electron charge. The electric force, called the Coulomb force, if you have two charges present, they exert forces on each other. The forces are equal but opposite. That's Newton's third law of motion. So I could write the force vector as KQ on Q2 over R squared times R hat, where this is the force vector. Its direction, R hat, is pointing away from the other charge. So if these are two charges with the same sign, both positive, say, or both negative, then on this charge, there would be a force directed away from the other charge. And on this charge, there would also be a force simultaneously directed away from the first charge. And the magnitudes of those two charges are equal, but the directions are opposite because each one is in the direction away from the other charge. So that's called Coulomb's law. K is a universal constant. It's the same for any two charges in the universe. Q1 and Q2 are the charges, which are measured in coulombs. R is the distance. So R is the distance. Think of these as little spheres. So R would be the distance between the two spheres, between their centers. You'll have to know the value of K, and you can look that up in the book. Now, the electric force is a field force. There's an electric field which exerts the force on a charge. So these charges don't really exert forces on each other. Each one creates a field, and it's that field that exerts the force on the other charge. The definition of the electric field at some point x is the force on a test charge divided by the value of the test charge. So Q here would be some number of some charge in coulombs. F would be a force in newtons, and you divide by the number of coulombs of the test charge. So you see the unit of electric field It's force over charge. It's newtons per coulomb. Or if you just had one source, charge Q, by Coulomb's law, the electric field produced by that source would just be KQ over R squared, R hat. So if you had one charge here, everywhere surrounding that charge, everywhere in the universe, everywhere in the volume around that charge, there's an electric field vector pointing in the direction of R hat. So these are the kind of equations you should have written down in your notebook as you were reading chapter 15. And these are the equations that we use in doing the homework problems. Now, the homework assignment this week is problem set 1. It's due tomorrow. It's due 1/17. So it's due tomorrow. And most students have already done quite a few of the problems. So let's go over an example. Here's one example from that assignment. The electric interaction is much stronger than the gravitational interaction for subatomic particles. You studied gravitation back in Physics 231. Now consider two protons, calculate the ratio of the forces, that is the electric force divided by the gravitational force. And as it says here, the electric force is much stronger. So this ratio, this fraction, the electric force divided by the gravitational force, will be a very large number with no unit, because the numerator has units of newtons force. The denominator also has units of newtons force. So if you take the ratio of two forces, you just get a pure number. Now, there's a general method for doing physics problems, which you should try to keep in mind when you're doing any of these problems. Step 1 is draw a picture and put labels on it. Step 2 is to write the relevant equations in your notebook. So when you start doing a physics problem, don't immediately start punching numbers into your calculator. Put your calculator down, pick up a pencil, draw a picture of the problem, label it, write the relevant equations. Now, you're not ready for your calculator yet. You have to look at those equations and see how to apply algebra to get an expression for the answer. And once you've got an expression for the answer, you're ready to pick up your calculator and put in the numbers. And when you calculate the numbers, you should also calculate the unit. So write it down with a pencil in your notebook. You know, what's the expression when you put in the quantities that you're going to use and include their units? Because if you keep track of their units, you'll automatically see what the unit is of the answer. So let's see how we can solve this problem using this general method. We start by drawing a picture. Okay, we have two protons. So here's one proton, here's another proton. We can label it. We can label what kind of particle it is. It's a proton. The other one's a proton. The distance between the two protons is r. So that's step 1. Now, step 2 is to write down some relevant equations. Well, we're going to calculate the electric force, so we better know the electric charge. The proton charge is called E, always. The mass is called M. I can look up E in the textbook, or I can just look it up on Google. if I Google what is the charge of a proton, I'll find E is 1.602 times 10 to the minus 19 coulombs. The standard unit of charge is the coulomb, abbreviated by capital C. And I could look up the mass. I could type into Google, what's the mass of a proton? Find 1.673 times 10 to the minus 27 kilograms. Of course, these are very tiny numbers because we're only talking about one single proton. No, I ready to calculate the electric force and the gravitational force. The electric force is K, Q1, Q2, so that's K E squared over R squared. Gravitational force, I remember from physics 231, is G, Newton's universal constant of gravitation, times m squared over R squared. And I'm supposed to calculate the ratio of the electric force over the gravitational force. So I take this quantity and divide it by this quantity. You see the 1 over R squared will cancel in the numerator and the denominator, have the same factor 1 over R squared in the numerator and 1 over R squared in the denominator. So those will all cancel. In the numerator, I'll have K E squared. In the denominator, I'll have GM squared. So that's the answer. No, because von Kappa will want a number. So now I have to multiply 4 numbers together. Now, if I just look at the numbers, K has a value 9 times 10 to the 9th in standard units. E has a number 1.6 times 10 to the minus 19. That gets squared. G, I mean, making a rough estimate, G has roughly the value 7 times 10 to the minus 11 in SI units. And M is this 1.7, let's round this off to 1.7 times 10 to the minus 27 squared. Now you see I have big powers of 10, so we could just look at the powers of 10. Here I've got, well, 9 divided by 7, I can approximate by 1, since this is just an approximation. 10 to the 9 over 10 to the minus 11 is 10 to the plus 20. Here's 10 to the minus 38 when I square it. Divided by 10 to the minus 54 when I square it. So I have 54 minus 38, that's 16. Combine that with a 10 to the 20, it's about 10 to the 36. So indeed, the electric force is much larger than the gravitational force for subatomic particles, in particular for a proton. It's 1 followed by 36 zeros. It's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on, so on, so on, until I have 36 zeros. So the answer will be a very large number. Now, do it more accurately than this. I mean, I've just made rough estimates here. Use a calculator to get these numbers accurately. And, you know, in the answer box, give the answer to, say, 3 significant figures. Here's another problem from problem set 1. A point charge Q is at a distance d1 away from a very large uniformly charged plane. The plane exerts a force F1 on Q. The point charge is then moved to a new location at a distance d2 from the plane, what's the force F2 exerted by the plane on Q at this new location? So I could draw a little quick picture here. Here's a plane, and it's charged. Let's say it's positively charged. So throughout this plane, there's charge. And here's Q. And I want to know, what's the force on Q? Well, positive charges repel each other. So all of these positive charges down here are going to repel Q. And so there'll be a net charge, a net force on Q in that direction. So that's the force. This distance is d1. This distance here. Then I'm going to calculate the force again, where Q is up here at a different distance. So maybe this distance is d2. It says assume the point charge is a proton. So I know what Q is. Q is E, 1.602 times 10 to the minus 19 coulombs. The problem tells me the value of F1 and the distance D1, 1 millimeter, and the distance D2, 4.7 millimeters. Now, if this were 2 point charges, you would know how to do this calculation. If this were a question of 2 point charges, you'd have Q at a distance R from another charge Q. Let's say both of them would have charge E. The force would be KQ squared over R squared. K is 9 meters squared per coulomb squared. Q is 1.6 times 10 to the minus 19 coulombs. That gets squared. Let's say this was D1. D1 is 1 millimeter. So that's 1 times 10 to the minus 3 meters squared. So this would be the calculation of the force if I had 2 protons separated by a millimeter. And the answer is a number with a unit. Don't lose track of the unit. Let's see what the number is. It's 9 times 10 to the 9th times 1.6 times 10 to the minus 19 divided by 1 times 10 to the minus 3. So here you have 1.6 squared times 9. Well, this would be almost 2 squared. So I don't know, this would be about 19. There's a power of 10 to the 9, 10 to the minus 38. Just making a rough estimate. I'd do it with a calculator. 1 over 10 to the minus 3 squared is 10 to the 6th. So that's the number. But what's the unit? Well, I have here Newton meters squared per coulomb squared times coulomb squared. So the coulombs will cancel. And I have meters squared in the numerator, and I have meters squared in the denominator. So meters squared will cancel. The only unit I have left is newtons. So the unit will be newtons, which is appropriate because this is a force. And the number will be 1.9 times 10 to the 10 minus 38 plus 6, 1.9 times 10 to the minus 23 newtons. That's a calculation you should know how to do. But that's not the calculation in this problem. Because in this problem, we don't have two small charges. In this problem, we have one charge and a charged plane. Let's think of that as a piece of metal, like a piece of copper, which is charged by some amount, and the charge will spread out over the plane. And I can express the charge in that case as the charge density, the charge per unit area. And charge per unit area, we use the symbol sigma, the Greek letter sigma. So now let's go ahead and do the homework problem. So step one, draw a picture and label it. Okay, here's the picture. I have a charged plane. I label it with the charge density sigma. I don't know what sigma is. That's going to be part of the problem. But I can label it. There'll be some charge density. Charge density is charge divided by area. If I have some amount of area, delta A, the amount of charge is delta Q. The ratio delta Q over delta A will be the charge per unit area, charge density. The unit for that will be charge in the numerator, area in the denominator, so it'll be Coulomb divided by meters squared. Then I have this proton, which has a charge Q, which I could just as well say it's E. At some distance d1 above the plane. Okay, now, what's the force on this proton? Well, remember, force, the electric force is a field force. There's an electric field due to the plane. So what is the electric field due to a plane with charge density sigma? And the answer is given in equation 15.8. Actually, 15.8 is the charge due to two planes. So the charge due to one single plane would be 1/2 of the answer in 15.8. 15.8 gives me the electric field between charged parallel planes. But I only want 1/2 of that. So if you look at the equation just above 15.8, you'll see the electric field is sigma over 2 epsilon 0. Epsilon 0 is another electric force constant, which you can look up in the book. And the direction is pointing away from the plane. So if we call the plane the XY plane, the direction away from that is the Z direction, where the unit vector K had. Now here's the electric field. That's E. It has to have a direction. Well, the direction is perpendicular to the plane. And it has to have a magnitude, which is sigma over 2 epsilon 0 by one of the equations in the book. So when you were reading the textbook, you should have written down that equation, sigma over 2 epsilon 0. Now the force is Q times the electric field. So the force is Q times sigma divided by 2 epsilon 0. Now I'm told what the force is. The force is given. So the unknown in this equation is sigma. So I can solve for sigma. Multiply both sides of the equation by 2 epsilon 0, divide by Q. Q is the same as E. So sigma is 2 epsilon naught F over E. Epsilon naught is about 10 to the minus 11 in SI units. F is given up here as 10 to the minus 13 in newtons. E is of order 10 to the minus 19. So you see, this is 10 to the minus 24 over 10 to the minus 19. Let's see, that would be 10 to the 19 minus 24. That's 10 to the minus 5. And the units, well, I didn't write the units down here, but I figured out a minute ago, the units have to be coulomb per meter squared. So in this answer box, I write down the value of sigma. And it's approximately 10 to the minus 5 coulomb per meter squared. Now you will want to calculate this accurately. So this is where you use your calculator. But you analyzed everything before you picked up your calculator. You didn't just start by punching numbers into the calculator. Now that's the first answer box. What about the second answer box? What if you moved the charge over here to a longer distance? Instead of 1 millimeter, make it 4.7 millimeters. Well, then what would be the force? Well, this is the force, no matter what the distance is. So in fact, for an infinite plane, the force doesn't depend on how far the proton is from the plane. All right, so let's go on to one more problem. Anybody want to ask a question? So here's one more problem from problem set 1. You have here two charges. Q1 is this one. Q1 and Q2 is this one. And Q1 is positive. It's in fact 1 coulomb. And Q2 is negative. It's in fact minus 1 coulomb. The picture is a little bit misleading because the picture here says Q is 1 coulomb. Here it says Q is minus 1 coulomb. Well, you can't have the same thing equal to two different things. If Q is 1 coulomb, then Q can't be minus 1 Q1. So I really should say this is Q1, this is Q2. And now the question is, what's the electric field at the green cross? So here's the green cross. What's the electric field at that point? Now, of course, the electric field will be a vector. It'll have an X component and it'll have a Y component. So there have to be two boxes to give the answer. One box for E sub X, one box for E sub Y. All right, now let's calculate this using this general method. Let's solve the problem using this general method. We start by drawing a picture. Well, we've already got a picture, but you might as well draw your own picture in your physics notebook. So let's draw another picture. You see, these 3 points define a rectangle. So let's just draw a rectangle. This corner down here is at the origin 0, 0. This point here is at 3 meters on the x-axis. So its coordinate is 3, 0. This position, the coordinate is 0, 2. And this has a charge Q, 1 coulomb. This has a charge minus Q. So I'll make this one red to stand for a positive charge. I'll make this one blue to stand for a negative charge. Now, the electric field at the green point will be the sum of two electric fields. Because when you have multiple charges, each charge has its own electric field, and the net electric field is just the sum of the electric fields of the individual charges. So there'll be an electric field for this one. I guess I called that. Oops. I called that Q1. And I called this one Q2. So here's Q1. Its electric field will be E1. Q1 is positive, so E1 points away from Q1. The electric field points away from the charge that's creating the electric field. So E1 will point in the X direction. Now here's Q2, it's negative. So the electric field for Q2 will point in the negative Y direction. The electric field points towards a negative charge and away from a positive charge. That's because like charges repel, unlike charges attract. If I put a little test charge here, call it little q, and make it positive, then there would be a force directed away from Q1. And the electric field is the force divided by Q, so that would be the force E1. Here, the force would be directed towards Q2 because this one's positive and this one's negative, unlike charges attract. So that's the first step. Draw a picture and label it. The second step is to write the necessary equations. So we should have an equation for E1. It's KQ over R squared. Now R, in this case, is 3 meters. This distance from here to the green cross is 3 meters. 1 meter, 2 meters, 3 meters. So here's KQ over R squared, and the direction is I hat. That's the unit vector in the X direction. And as for E2, it'll be in the negative direction. KQ, Q is in both cases 1 coulomb, divided by this distance squared. What's this distance squared? Well, it's from y equals 0 to y equals 2, so it's 2 meters squared. This distance is 1, 2, or this distance is 1, 2. And it'll be in the j hat direction, or actually really the minus j hat direction. So you have to be a little careful about the signs. Q1 is a positive charge, Q2 is a negative charge. All right, so those are the necessary equations. I figured out electric field 1 and electric field 2, and now the answer will just be the sum of the two vectors. E1 plus E2 will be the electric field at the green cross. Now, I want to know what's the electric field in EX direction, because I'm going to put here EX. And I want to know the electric field in the Y direction, because I'm going to put here EY. Well, E1 is in the X direction. So EX will be KQ over 3 meters squared. But E2 is in the, well, actually the negative Y direction. So the Y direction for the sum of these two, E1 doesn't have any Y component. All of the Y component is in E2. It's minus KQ over 2 meters squared. Now let's estimate the number. I mean, you're going to do this with your calculator, but let's just kind of get an estimate. K is 9 times 10 to the 9 with a unit. Newton meters squared per coulomb squared. Q is 1 coulomb. 3 meters squared is 9 meters squared. So now we have a number with a unit. The number is 9 times 10 to the 9 divided by 9. So the number is 10 to the 9. The unit is Newton meters squared divided by meters squared. So the meters squares cancel. Divided by Coulomb squared times Coulomb. So there'll be 1 power of Coulomb in the denominator. And then Newtons in the numerator. So EX will be 10 to the 9 Newtons per Coulomb. And Newtons per Coulomb is one way to express the unit of electric field. We'll later learn another unit, the voltmeter. No, volt divided by meter. But for chapter 15, we can think of the unit of electric field as Newtons per Coulomb, because electric field is force divided by charge. Force is Newtons, charge is Coulombs. Well, that's EX. Now what about EY? Well, that's the E2 part. That's the part that's pointing in the Y direction, or actually the negative Y direction. So that's minus K, 9 times 10 to the 9, Newton meters squared per Coulomb squared. Q is again 1 Coulomb, 2 meters squared, and the denominator is 4 meters squared. So again, I have a number with a unit. Let's figure out the unit first. I have Newton meters squared times Coulomb divided by Coulomb squared divided by meters squared. So that'll be Newtons per meter. So that's the appropriate unit. And what about the number? Well, it'll be minus 9 divided by 4 would be 2.25, and the power of 10 times 10 to the 9th. So that's what I write here and here. Okay, any questions about these problems or any of the other problems that you've been working on from chapter 15? I don't see any questions on the chat board. Anybody want to just unmute your microphone and speak up a question? Here's a question on the chat board. Do you not need to include the plus 0.24 and minus 0.24? Where is plus 2. Where is plus? Oh, yeah, you do. This would be the answer if the charges were minus 1 Coulomb, plus 1 Coulomb, and minus 1 Coulomb. So this would be the answer for the picture. But use this data, which will be different for your problem, but everybody will have a different value for Q. Don't use 1 Coulomb and minus 1 Coulomb. Use, in this case, 0.24 coulombs and minus 0.24 coulombs. So you see the electric field is proportional to the charge. Just take this number and multiply it by 0.24. And similarly here. So yeah, on a lot of these problems, there's a picture, but you will be given a different data value for which to do the calculation. Any other questions? Or any questions from the other problems in chapter 15? Okay, well, if there aren't any questions, remember we'll have a Zoom meeting like this with some hints for some of the problems every Monday at 7 p.m. So now I will stop the recording. Oh, here's another question. I have a more vague question. The first equation you showed, I don't have in my notes. And I can't find it in the textbook. Do you know where that is? Do you mean this? Q is NE. Well, if you look at chapter 15, you'll see that if you look on table 1, table 15.1 gives the charge of a proton. The charge of a neutron is 0. The charge of an electron is negative the charge of a proton. So that defines E. So that's where E is defined in table 15.1. Now, there are some elementary particles called quarks, which have fractional charge, but those aren't really part of an atom. Those are parts of the interior of a proton. So if you just consider an atom, which consists of protons, neutrons, and electrons, then the electron charge, the charge from the electrons will be the number of electrons times minus E. The charge from the nucleus will be the number of protons times plus E. If you look on page 315, it talks about quantization. The bottom of page 15, it talks about quantization. So if you look at the very last sentence on page 315, it says, it's remarkable that the proton and electron, although very different in mass, carry charges of exactly the same magnitude, plus E for proton, minus E for the electron. All charges come from those elementary particles, elementary subatomic particles. Any charged object has some mismatch between the number of protons and the number of electrons. Okay, so taking about 45 minutes, the Zoom meeting should take around 45 minutes. So let me stop the recording.